this section, we're going to talk about uh, a concept called belt friction. So this this concept, we say belt friction, but it actually means something a little more than just belt friction. It basically any sort of rope or cord basically wrapped around something to create, and then you ask the question, how much force does it take to cause it to slip? Is is uh, is in the realm of belt friction. And so we have a couple of examples here. So the first one, this is a winch on a sailboat. So in if you were to use this, basically what happens is a cable comes in. So this is a rope that's attached to a sail, comes in here, and it gets wrapped around this winch body. So this is the winch body right here, and then you put a handle in right in this place, and then you basically turn it. And you turn that handle, and it causes the winch body to turn, and then you either pull in or you can let out rope to trim the sails, for those of you that have ever sailed. A maybe more technological applicable is flat belt power transfer. This used to be very popular in the early 1900s when you would have central steam power or something of that nature. It's fallen a little bit on the wayside due to the cheapness and availability of large electric motors. But here you can see an electric motor right here. And then this is a big flat rubber belt that's providing power transfer, right? So this turns here, and the connection of the belt causes this thing to turn right here. And so the question you want to ask here is how much force, how much force does it take for the belt to slip? Right? Because that's a practical limit for both of these situations, right? In this one, the practical limit is I can only put so much torque here before this belt starts slipping and I don't transfer power. And in this one, I can only pull on it, so only so much force can be pushing this way, right, before it starts slipping off this drum, this winch drum, and I lose the trim of my sail. So for those of you who have any sailing experience, this is cool. For those of you that are more interested in machine design, this is cool. I think they're both cool, but I do both. All right. So let's analyze this situation. So what we'll look at, or what we'll think about, is we'll think about the belt transfer situation. So here's again, right? We have a motor with a big flat belt powering a large wheel of some sort, and we can see here this is sort of the model, right? So this would be the motor. This would turn this direction, and the idea, right, would cause this then to turn in that direction. And so the question is how much force can you put on here before this belt starts slipping over this drive wheel? And if the belt's slipping over the drive wheel, you're not getting good power transfer, and you're not doing what you want to do. Ooh. Sorry, lost the whole sketch window there. All right, so let's do it. So here's the top port. So again, what we're sort of interested in is we're interested in the power part. So the transmitter was down here, and what we'll do is we'll think, all right, so here's sort of the belt that's sitting on top of this, right? And we've got two tensions, right? So there's a tension 1 over here and a tension 2 over here, right? And we're going to say there's a potential that the impending motion is this way, right? So this belt is we can imagine that it's pulling down, and what's going to happen is ideally we're going to ask the question, when does this slip to the right? So in this case, if you think about it, T1 will be less than T2 if we're going to slip this way. All right, so that's where we'll start from. What we'll do is we'll draw a free body diagram of a little piece of that. We'll talk about two critical components, right? So there's the radius. This angle right here will denote beta, and beta will be the contact angle. So you'll remember from the previous one that our contact area, or the amount of stuff in contact with the ground, didn't matter for friction. In this case, it does. So for the case of stuff just sliding on the ground, doesn't matter. In this case, very important. How much contact area you have is critical in determining how much friction, and in some sense, how much power you can transfer from using flat belts. Okay, so we'll draw a free body diagram of a little section of the piece, right? So here's a small section of the belt. Ooh, not very vertical. So Here's a vertical line, and then our horizontal line coming off, right? So here we have sort of X, right? And here we have Y. Great. We've got tension T on this side, and then tension T prime, which is equal to the tension on the left side plus some sort of small tension change due to the fact that we've effectively got a delta theta here. And as good engineers, we know when we have a delta theta, that means we're driving towards a derivative or an integral type process. So we're impinging motion to the right, so our friction is this way, and that is a delta friction. And then again, we have a small amount of delta N, right? So we have a delta friction going that way, and a delta normal force pointing up. You can find out that if you do the geometry, that this angle right here is delta theta over 2, and this angle right here is also delta theta over 2. Great. So here we have our free body diagram that we've got all set up. I'm gonna copy that, and then we'll do our analysis based on that thing. So there's our free body diagram. I'm gonna erase all of this stuff, and then we'll move to a new slide here. All right. So here's our chunk of stuff that we're interested in. It's not letting me move in. Come on. That's interesting. Oh, yeah, I know why. There we go. Plugged it into the wrong thing. Okay, sorry about that. Okay, so here we go. So here's our free body diagram. We've lost our x-axis. I'll put it back in. All right, there we go. All right, sorry about that. So now we'll attack this, right? Some forces in the x. All right, we're going to have t plus delta t, right? And then cosine delta theta over 2 minus t cosine delta theta over 2, and then minus delta f equals 0, right? So portion of the tension in the x direction, portion of the other side of the tension in the x direction, and then the small amount of friction that we have. And again, we assume that to be horizontal because our angle is very, very small. All right. Some forces in y. So here we have our normal force, right? And then we'll have our two downward portions of that force, delta theta over 2 minus t plus delta t sine delta theta over 2 equals 0. Awesome. So there we go. Where we don't want, right, we want information on our friction and our tension, so we're going to solve for delta n. And delta n we get equal to t plus delta t, just basically rewriting this right there, sine delta theta over 2 plus t sine delta theta over 2. There we go. And then we can substitute in and get ourselves the equation t plus delta t. Again, those are tensions plus small amount of tension. Cosine delta theta over 2 minus t cosine delta theta over 2 minus our friction point mu s, and then this thing, right? So t plus delta t sine delta theta over 2, and then plus t sine delta theta over 2 close, all equal to 0. All right. So what we've done here, right, is we've drawn our free body diagram, we've written our two force sums, we've solved for n, we've plugged that back into here. All right. And what I'm now going to do is I'm going to take this and I'm going to rewrite it. So I'll basically sort of massage this into a new form, one that we can actually deal with. Oops. not what I intended to do. All right. So we're just going to clear this out, and then I'm going to write the rewritten version of that. And what we're going to find is we can rewrite that as delta t cosine delta theta over 2 minus mu s 2t plus delta t sine delta theta over 2 equals 0. All right. So here, right, we divide by delta theta. And say delta theta goes to 0, and that gives us the differential equation dt d theta equals minus mu static times tension equals 0. All right, so this is our governing law, and we can kind of see that right when as delta theta goes to 0, cosine goes to 1. Delta t also goes, again, right, deltas are going to 0, so that becomes that. So this becomes t. Our delta t goes to 0 as well. So I'm sorry, our delta t also goes to 0 because the tension goes away, or it just becomes t. Those drop out, right? And then our sine delta theta over 2, we have it over delta theta, and that's sine theta over theta, basically. We can write that out. Okay. So we have this sort of complicated looking thing. It's a differential equation. It's a first order differential equation. It is quite simple to solve once you know how. And what we find is that the solution to that differential equation is natural log of t. So the way that we solve this differential equation, I should say this, is we basically just integrate it. All right, so we'll get rid of that. We'll integrate that. So we'll rewrite this as dt over t is equal to mu s d theta, basically just dividing out. We'll go from 0 to our contact angle, and we'll go from t1 to t2. dt over t, natural log. This is simply theta, and so that gives us natural log t2 minus natural log t1 equal to mu sub s beta. And this is our relationship. That's what we were looking for, and that's what we're interested in finding. We can modify this, rearrange it a little, and what we get is our two belt friction laws. So these are our belt friction laws. So belt friction law, and it is natural log T2 over T1 is equal to mu s beta, or T2 over T1 is equal to E mu s beta, right? And these are the same things. We've just done that in the case here where T2 is considered to be larger than T1. And that's based on our discussion about impending slip, right? So we set up T2 on the right-hand side, and we set it slipping towards the right-hand side. And so that is that. Those are our belt friction laws. These give you the relationship between the friction on one side, the force on one side, and the force on the other side. It depends, not unsurprisingly, on the static coefficient of friction, as well as the contact angle, or how many times you wrap this around. Beta must be in radians. So 360 degrees, 2 pi, right? So keep that in mind. So must be in radians. And that's pretty much that.